solving a system of equations using the elimination method. Before we can look at the elimination method and how to solve a system of equations algebraically, I think it's really important that we take a look at a visual representation. So when you're solving a system of linear equations, you're actually looking at two lines in space. So those two lines are going to cross at one place. Is it possible that they don't? Of course, there's always going to be special circumstances, but most of the time they're going to cross at this one location. And that's really special because that's the one place in the world that this blue line and this green line both exist at the same time. So that's what this solution is. So let's mark that down. This is the solution. And because it is a coordinate point, it should have an x value and a y value associated with it, right? Coordinate points have x's and y's to represent the location. So now that we got kind of a visual and we can see that it's a point, it's where two lines cross, let's take a look at the algebraic examples. So if we're going to use the elimination method, we're going to have a very specific goal in place. And our goal is going to be this. We want to be able to add and eliminate. So what that means is I want to be able to add these two equations together. And when I do that, I want to be able to eliminate one of the variables, okay? Because I can't solve an equation with x and y's. If I solve for x, there'll still be a y. If I solve for y, there'll still be an x. It'll be a mess, right? So I want to be able to add these two equations together in such a way that either the x's go away or the y's go away. So if I take a look at these x's, right, and these y's, one should be speaking to me when I look at those coefficients in front. And that should be the x's, right? If I multiply 3, I can get to 6. I can make them be the same. 4 and 3 is a little bit harder. That's why I'm going to stay away from the y's. It's not impossible. It's just a little bit more challenging. But those x's, they're screaming to me, right? I can just multiply that bottom one and I'm all set to go. So let's do that. I'm going to multiply the bottom equation by 2. And I'm going to do that because if I multiply the bottom equation by 2, both my x's in the top equation and the bottom equation will be 6's. But remember, I don't want to get them to be exactly the same. I want them to reduce to 0. So it's really important that they have different signs. So I'm going ahead and make this negative. So now that I have a negative 2, I'm going to multiply every term of this bottom equation by negative 2. So 3x times negative 2 is negative 6x. Negative 4y times negative 2 is positive 8y. And negative 21 times positive 2 is positive 42. So this whole bottom equation transformed to be this guy because I multiplied it. And I want you to denote that I multiplied every single piece of this equation on both sides of the equal sign. And that's how I got all of my expressions over here. All right, now I'm not going to change my top equation. I'm going to leave that guy exactly the same because I changed the bottom to be able to meet with him, right? So now I'm going to leave it as 6x plus 3y equals 24. Now take a look at that because look what I did with my x's. They have the same leading coefficient. The only difference is one's positive and one's negative. So check this out. When I go and I add these two equations together, my x's are going to reduce. They're going to add to 0, which means I have no more x's. And that's huge. That's huge because now if I add together my 3y and my 8y, I get 11y. And if I add together my 24 and my 42, I get 66. And this is great because this is an equation I can solve. I can get y by itself because I no longer have an x value. If I divide both sides by 11, now I have y equals 6. And that's absolutely phenomenal, okay? So now I have half of my solution. So let's mark this down. Solution, I'm so excited. I have my y value. But remember, a solution has an x value and a y value. So I know that my y is 6, but I still need to find out what this missing x value is, okay? And the only way to do that is to take one of my original equations, plug in what I have for y, and see what I get for x. So it actually doesn't matter which equation you use. So I'm just going to use the top one. So I'm going to use this 6x plus 3y equals 24. But again, it doesn't really matter which one you use. And I'm going to take this y, and everywhere I have this y, I'm going to actually put the 6, right? So 6x plus 3 times 6 equals 24. And I just noticed there's a lot of 6's. So just to be clear, that y was replaced with the 6 from the solution. So this is here because of this 6 here, okay? Now I'm going to simplify. So if I bring it down, 6x plus 18 equals 24. If I subtract 18 from both sides, I end up with 6x equaling 6. Divide both sides by 6, and I have x equals 1. Okay, x equals 1. So that means that my solution is going to be the 0.16. If the question asked for the x coordinate of my solution, I would say 1. If it asked for the y value, I'd say 6. And if it asked for the full solution, I'd say 1, 6. Okay? So this, again, is if these two lines were crossing on the coordinate plane, where would they cross? The 0.1, 6. Remember, you can always check the solution to a system of equations using your graphing calculator. If you're curious about how to do that or any other calculator tricks, please log on and find the other video on the channel which talks about TI Inspire and all the calculator tricks associated with it.